Good afternoon and welcome to this seminar in the series of the Department of Epidemiology. Also welcome to those of you who are online. It's my great pleasure to introduce our speaker of today, Dr. Issa Dahabreh. Dr. Dahabreh is Associate Professor of Epidemiology and Biostatistics here in the Harvard School of Public Health. He's also Section Head for Epidemiology and Data Science in the Smith Center for Outcomes Research in the Beth Israel Deaconess Medical Center. And you will show that later, his research focuses on design and analysis of observational studies and randomized trials, emphasis on causal inference and evidence synthesis. Dr. Dahabreh, great to have you. I give you the floor.
Thank you.
Speak about toward harmony between trials and observational studies.
Thank
Trial augmentation using external data and models. Just to show you that I can read.
It is a long title. It is a long title. Hello, I'm Issa. So these talks, I find, have a couple of challenges. The first one is I am kind of expected to give the big picture, but then if I'm on the other side, just the big picture never feels satisfying enough. And so I tried to briefly talk about what I've done and what I hope to be doing, but the bulk of the presentation I chose to make it about a specific area of research, especially one that we think we're very excited about. The second challenge is not everybody likes the mathematics. This is a challenge because I'm going to make statements that they come very close to saying I can offer free lunches. And there is a certain subset of us here, a sizable subset, that feels very uncomfortable with free lunches without any documentation. So I had to bring some receipts in the form of technical arguments, but I will hand-wave enough that it should be pleasant for everybody, and then the technical details are not important. There's also a lot of supportive documents for people who want to dive deeper. So with these caveats, let me start. So the thing I will spend most of my time is trial augmentation there in the middle. But as I said in the beginning, I'll talk a little bit about this framing of the combining of information from diverse sources as an explicitly epidemiologic activity, and how this works toward perhaps a better or increased harmony between different designs. And then at the end, I'll spend a little time talking about what we hope to do in the next few years. Okay, so the set of problems that I tend to focus on are problems of combining information, but with specific goals. So the information comes from multiple and diverse sources, and the goal is to learn about parameters in a specific target population, often but not exclusively causal parameters, like a treatment effect. I think this focus on a specific, well-defined target population, possibly different from the population underlying its component source, is what makes this a paradigmatic epidemiological activity. Because I take epidemiology to be the part of applied math and biostat that focuses on specific human populations. And then taking a step back, this kind of activity has a huge, very long history. In the 90s, there was the idea of cross-design synthesis, and I had the privilege of talking to the department a few years ago on this topic. But arguably, even case control studies, specifically those with a secondary study base, are a very early instance of combining information, since the study base and the cases are sampled often from separate sources, and one requires sampling and causal arguments to put them together. So what is new in what I will try to talk about? I think there is an extra causal and sampling model formalism. There is transparency about assumptions in a way that only formal causal and statistical models allow. And then there is some improvements, we hope, in the way we estimate things, including by allowing the use of modern, very data adaptive estimation methods. Think machine learning, AI, and the like. In terms of an overview, my work, and I focus here on the last 5 years that I've had the privilege of being in the department, focuses on identification and estimation of target population effects. One contribution that we think is unique to our framing is that we treat the participation act, the act of participating in a clinical trial, as an intervention in itself, and therefore allow for engagement effects and for a theory of identification that allows for the trial process to affect the outcome through paths separate from the randomized treatments. Other contributions have had to do with creating a toolbox of study designs that can be used for generalizability, creating a typology of designs that capture the relation of the trial with the target population, sampling methods for the non-participants, and what we call partially nested designs that allow for efficient use of existing data to learn about broader populations. Other contributions have had to do with alternative identification strategies that focus on weakening assumptions by exploiting the very common clinical belief that relative effect measures are more likely to be transportable than absolute effect measures, focusing on different estimates, including estimates that address heterogeneity, and that's particularly relevant for target populations, since many times those include subgroups of individuals that are grossly underrepresented in trials. The handling of complex data structures that come up when you have clustering or other pragmatic elements that usually associate with complications like loss to follow-up and non-adherence, and then extensions of the methodology from clinical trials and treatment effects to address factual and counterfactual prediction. A second theme has been what I call causal interpretable evidence synthesis. We introduce a new version of meta-analysis that aims to have a causal interpretation that is explicit and supported by assumptions that are now open to critique. We extended these ideas to explore very severe missing data and partial data issues that come up when one attempts any kind of meta-analysis, any kind of synthesis over studies. We dive deeper into something that we call benchmarking and joint analysis, which is a formal comparison between trials and observational studies as a precursor to using the data together, where our focus has been on highlighting that one needs to be very careful about aligning estimates, designs, and populations before proceeding to any kind of comparative or pooled analysis. And with a little luck, we've had the opportunity to do this in more and more applied settings, including a fairly extensive program through the Smith Center that is slowly coming to fruition with several applications of the methods into new pharmaceutical and primarily medical device trials using either Scandinavian or United States registries to define target populations. And I like to think of this as a program that tries to use the formalism to create some harmony among designs, and this is where I got in trouble about 2 years ago. The trouble, I think, was twofold. One source was internal. I looked back at this work and I thought, I don't know how often I fully believe all the beautiful assumptions that we were able to write down. The second source of trouble was external. I had the opportunity to talk more with trialists because some of my methods were shifting to being used with actual interesting clinically recent trial data, which necessitated more intense communication with the people generating the evidence. So it was no longer an abstraction that I could just see through an already collected data set. They were humans, and the humans were telling me, these assumptions are a little tough to swallow. Why would we put at danger our beautiful, pristine, randomized trial? Now, the way we resolved this, the team helps, of course, but it's an internal process as well. And so the way we resolved this difficulty is by working under weaker assumptions, but also shifting maybe the focus of the technical development to address the uses, the needs of the trialists. And this is what led to what I want to focus most of the time today, which we call trial augmentation. Before I talk about the exciting technical things. I just have to call out certain people. These are the people just for this narrow line of research. Pierre and Ricard are very soon to or just graduated PhD students who visited our group from Europe. Guambo, who was a postdoc here and now is a professor at Dartmouth. Wen Ling, who still owes me some analysis. Joking, just joking. It's okay. Andrea, Gabrielle, and Philippe, collectively called the ETH guys, who have done a lot of the machine learning and mathematical development of some of the things I will present here, and of course many more senior colleagues and collaborators. Okay, so why do I want to talk to you and why am I so excited about trial augmentation? Everybody knows that randomized trials are time-consuming and costly. And as I was saying before, a lot of our trialist friends express deep skepticism about the strong assumptions that may be needed either for target trial emulation, which everybody here is familiar with, or for the joint analysis that I have advocated for. And so these ideas are good for improving research economy and statistical efficiency under assumptions, but they require those assumptions. And so the question we posed, or perhaps the question we were forced to pose by our collaborators is, can we leverage the beautiful, rich, growing in size external data to improve trial efficiency, but can we do that without sacrificing the causal guarantees of randomization? And so the goal, as we understood it, was to reduce sample size for the trial conduct, keeping, let's say, the power or precision the same, but guaranteeing valid statistical inference, even if the external data, even if the observational data that are going to be brought into the analysis is misaligned with the trial. Misalignment here can mean severely confounded, subject to differential strong measurement error, or impossible to model out with the available tools in a way that captures the true associations. See, I told you it was going to sound like a freelance. So bear with me for what follows. Okay, so I need to create a little bit of a setup to be able to solve the problem even in the simplest case. So I'm going to think in the most simplest situation we can handle. So baseline covariates X. I'm going to treat Y as the outcome, and I'm going to think that the outcome is measured at the end of the study. I'm going to use capital A for the treatment, which in the trial is randomly assigned. And then, as we usually do to talk about causality, I'm going to think about two counterfactual outcomes, since my treatment is binary, the Y superscript 0 and the Y superscript 1. And those are going to be what would happen to the person had they possibly, contrary to fact, received treatment 1 or treatment 0. I call this a simple, perhaps oversimplified example, because I'm not going to be talking about censoring, incomplete follow-up, missing data, measurement error, except to say that if it exists in the external data, it doesn't matter. My only justification for these simplifications is that it's kind of messy and requires a lot of technical footwork to do the harder cases and also get the concepts across. So, in the words of Marcelo Pagano, trust me, I'm a doctor. If the basic case works, we can do the complex case with censoring, non-adherence, loss to follow-up, and so on and so forth. Okay, so my data are going to be just the observable parts, so the X, the covariates, the treatment, and the outcome, and I'm going to think they come from some distribution, and I impose no restrictions on that distribution, except that the treatment is randomized in the randomized part of my data. And so my task is to estimate the average treatment effect. This is just the average of the difference of the potential outcomes. And so I'm just going to compare what happens if everybody were to be treated and if nobody were to be treated. Now, in this room, I feel I don't need to say, but under some standard assumptions, these three that I have here, the first one is consistency. It just means the outcome that I get to see, the observed outcome, if you receive a particular treatment, is equal to the counterfactual under that specific treatment. Randomization, where everything is independent of treatment, and just positivity, where everybody has a non-zero probability of getting the treatment. Under these assumptions, two of which, randomization and positivity, are essentially guaranteed by the design, and consistency can be supported by making specific design choices. Under these assumptions, my causal parameter is equal to just a crude mean or risk difference. I can just run my trial, compare the two groups at the end of the study, and be happy. Have a good, consistent, and reasonable estimator. In fact, a lot of theory, and I will summarize some of it soon, has actually concluded that without assumptions beyond those justified by randomization, in the simple case that I am solving, we can create covariate adjusted, model robust analysis that are the most efficient approach for estimating the average treatment effect in large samples. This theory is beautiful, unfortunately is not mine, and I will highlight only the parts of it that we need today. The big idea of covariate adjustment, as I will present it, is that I want to have a predictive model, call it H hat, that I can use it to predict counterfactuals for each observation. So I'm going to want to use my model for the treated people to find out what would happen had they been untreated, and for the untreated people to find out what would happen had they been treated. It turns out, as usual, Jamie had thought very deeply about this problem. And so in the 90s, you could see immediately from the work on observational data and missing data problems that you can also create a trial-appropriate estimator that uses this predictive model in this specific way. The formula is not important. It will be familiar to those who know about doubly robust estimation of treatment effects with one tweak. What's important is that I combine the observed treatment and observed outcome, and this is the people who get control treatment and their observed outcome, with these predictions in a smart way, and I will explain in a second what it means to do it in a smart way. But what is really important to note, and this is the only little tweak from Jamie's theory here, is that we use the true probability, we use the true probability of assignment into the treatment groups. That's the only difference from the usual AIPW for observational data, where you use the so-called estimated propensity score. But other than that, this is just AIPW applied to the trial, where we are taking the little tweak of using the true probability of assignment. Now, how are we to proceed to find these regressions? How are we to estimate these terms? The usual way we do it is we estimate some kind of model for the outcome using the trial data alone. This looks complex and annoying, but you can think of it as any kind of popular method. You can think of it as solving the maximum likelihood for an outcome regression in the arms of the trial. So we get that model, we estimate that model, and we plug it into the formula that I showed here. We put the estimated parameters, if we are using logistic regression, to get these predictions under treatment and under no treatment. And so again, it's a classic result, only with small modifications needed to use the true probability, that you can construct, if you do it carefully, an estimator that is finite, sample, and biased, which people who like trials love, and also with good large sample behavior, specifically an estimator that goes to the true value as the sample size increases. It's asymptotically consistent, asymptotically normal, and it has some variance that we can get a handle on. And it turns out that the smallest variance will be had if the model that you use here for H is a model for the outcome regression. So if one were omniscient and knew how to estimate the true outcome regression, they would have the most efficient estimator under the assumptions I laid out. With extra assumptions, the sky is the limit, of course. Okay, now this is a beautiful result, mostly due to Jamie and his collaborators from the 90s, but it has a small difficulty in practical application. This is, I sometimes say, the statistical equivalent of in the long run we are all dead. In the long run, trial budgets run out. So the idea is that the optimality piece of the result, the smallest variance, the greatest efficiency, is achieved if you get a good quality outcome regression. The outcome regression is not necessary for the estimator to give you the right answer. For consistency, for unbiasedness, the outcome regression is not necessarily correctly specified. But to get the efficiency gains, you have to get truly close to the true outcome regression. And the problem of trials is that they tend to be relatively small, and so it's not easy to estimate good models for the outcome using trial data alone. In other words, you need a good model, but it's hard to get it using the trial only. So what is a solution? A solution would be to use rich, increasingly available external data and models to supplement the evidence in the trial. So the idea would be to use prior trials. Those tend to be a good source because they tend to be reasonably aligned in terms of their measurements with the trial data. But you could imagine using registries, electronic health records, claims, any source that seems appropriate for the context. But what we want to do as a sketch of the overall approach is we want to exploit randomization so that we maintain robustness in a way that doesn't invoke any additional assumptions beyond the ones I showed in the slide before. So I am not going to require the external data to be unconfounded or measured perfectly or anything like that. Still, I'm going to try to use the external data to improve efficiency. And my idea is that in the external massive data sets, I may be able to do much more adaptive, aggressively flexible modeling. Think machine learning, AI, whatever is your favorite approach. And so I'm going to use the external data for that, and then there is a possibility of adapting it to the trial that I won't cover because it creates even more technical content. But even without any adaptation, I just estimate regressions in the external data, and I will find a way to use them in the trial. Okay. So, again, I'm going to learn the model in the external data, and that's really a benefit for some audiences. For example, because several sponsors have expressed interest in using these methods in designing and analyzing new trials, we've had the pleasure of interactions with the FDA on specifically discussing the adoption of the methods for registration trials. And so the FDA is exquisitely concerned, I think appropriately, with the potential for using data adaptive methods to look repeatedly at the data. And so there's this beautiful thing here that you use the external data even before the trial starts. You lock your prediction models, and then you can deploy them in the trial in a completely pre-specified way. And what I'm going to do, here's the strategy of the technical things. All the remaining 10 or so slides are going to be just putting flesh on the bones of this two-bullet strategy, is I'm going to combine the estimator we saw before, which uses only the trial data, and another estimator that looks very similar, except the regression functions are estimated data adaptively in external, rich, large-scale data sets. And then what will I have? Well, since I'm using the true probability of treatment, I will have two, if done carefully, unbiased, consistent, asymptotically normal estimators. But I don't want to have to choose, and the trial size may be small enough that choosing is not easy. So instead, what I'm going to do is I'm going to develop a combined estimator that uses the two, the trial only and the one that exploits the external data. I'll call this one the combined estimator, and it will be such that it is guaranteed to do no worse than each of its components. Because of this result, it is guaranteed to be no worse than the best of the two components, which means that if the trial-only estimator was great, this will be no worse. And if the external data proves to be useful, you were lucky. You found a good data set with rich information. In that case, you're going to do no worse than using just that optimal estimator in large samples. And in fact, I'll show a little bit of evidence on how the procedure adaptively decides how much to rely on the external data versus the trial data. Okay, so this is the sketch of the method. We aimed for generality, so I'm going to assume that in addition to the trial data, which is up here, the analyst, the trialist, has access to at least one, possibly multiple, external data sets. And then in those data sets, a separate external model is estimated. The simplest case is you have one external data set and one model. In other cases, you have one external data set and multiple models because you have different algorithms that you want to try. In other cases, that you have multiple external data sets and one favorite algorithm. And the general case is that you have a lot of data sets and a lot of models that you want to try, and you can cross all of them together. Somehow you end up with k pairs, if you will, of data and models. And those are estimated in the external data. So when you go to analyze the trial, you are working with something that is fixed, is not being chosen using the trial data. Okay. The other thing that you do is you do a regression in the trial. That's what we expected from the basic AIPW estimator that I showed. So now you have k for the new data sets and models down here, plus 1 from the trial, k plus 1, different outcome regressions. The trial only one, and the ones that you estimate in the external data. And then what you do is you take the AIPW estimator that I showed you, that scary thing with the sums that puts together the true probability of treatment and the regression, and you evaluate your models, and you get a different AIPW, if you will, for each of the models. You get the trial-only AIPW, which is the efficient estimator if you make no additional assumptions in large samples. And then you get one new estimator where you're just replacing the trial regression with the externally estimated regressions. So now you have k plus 1 estimators of the treatment effect. But you don't want to pick, you want the data to inform you. You wouldn't know how to pick in finite samples. So what we're going to do is we're going to create a linear combination of the k plus 1 different results, and we will have a single estimator. And again, this kind of meets the needs of our envisioned end users, because they get to see a single result with a single standard error and a single hypothesis test on that. They don't have to do anything like a separate hypothesis test, which would induce multiplicity concerns. Okay, this is the description, and this is the big idea. We're going to take a linear combination, and so for a second, work with me and suppose that I know the correct weights. So this lambda, which is the weight for the linear combination, for a second, suppose it were fixed. So if the lambda were fixed, and I made the constraint that the sum of the lambdas would have to be equal to 1, I have a unique single estimator for every set of lambdas. Let me say two things. Number one, it sometimes helps to think of this in the case where you only have 2. Again, we were struggling for generality, so we're doing an arbitrary number, but imagine that you have 2, then all you're doing is lambda times the trial only, plus 1 minus lambda times the external one. If you have more, then you just sum them up like this, and you make sure the weights sum to 1. Now, why do the weights have to sum to 1? That's crucial so that you can still get finite sample unbiasedness in your analysis. There is another interesting thing that happens. Because the big scary estimator that I showed you is completely linear and additive, if you push the lambdas inside the sums, you end up getting a single estimator at the end that just has a linear combination of the regressions. It has a linear combination of the predictions. So you can think of this as just one grand AIPW estimator, again, the formula we saw, but inside it, instead of using a single regression model, I'm using a linear combination of the regression models. Why is that nice? Well, since the lambdas are fixed, and this thing has the exact form of the AIPW, then I immediately inherit all the properties of AIPW. I am consistent, asymptotically normal, robust to misspecification of the regression. So if my lambda choice was bad, or if my H hat was terrible, or if my F hats were irrelevant to the trial where, my Fs, sorry, were irrelevant to the trial where I apply them, I would still get a robust, asymptotically normal estimator that I can do inference. So there now remains only one problem, I think. The problem of choosing the lambdas. If you view this as a minimization problem, you might want to pick the lambdas that make the variance of the thing the smallest. Why? To make sure you have the biggest power, the highest precision in your results. The solution looks a little complex, and it requires estimating the variance, covariance matrix for the estimators, but this is a solved problem. And in fact, in the 2 estimator case, this becomes just a simple quadratic problem where you just have to pick the smallest point, the lowest variance. So you can solve this with an exact closed form solution, which happens to be this. So what is the problem? The problem is it depends on the variance covariance of the estimators, which is not known, and so we have to estimate it. What is the good news? The good news is that hundreds of years of statistical theory give us a way to get consistent estimators of this sigma hat. So basically, we will empirically estimate the variance, covariance of the estimators, and we will use that estimated covariance to obtain the pooled estimator. And what's an interesting result in a paper with too many authors whose last name was D, starts with a D, is that this estimator is consistent and asymptotically normal. And in fact, it has the same variance. The estimator with the lambdas estimated has the same asymptotic variance. It's asymptotically equivalent, actually, to the estimator with the optimal lambda. Again, this comes from the fact that we know how to estimate variances and covariances. So we estimate them really well, and they make the estimated thing in large samples behave as well as the true thing, which we don't know. So that's how we solve the problem. And this is the asymptotic freelance that I promised you at the beginning. It turns out that this variance of this combined estimator is less than or equal to the smallest of the variances of the component estimators, which means, informally speaking, that it is never worse than the best of them. So that's the guarantee. It will be never worse and usually be better, because the point where they are all equal is a very special situation. It doesn't happen. Okay, so freelances have been promised. I will now attempt to deliver some of them. First, I will show some simulation studies. I don't think anybody would be too excited to read my simulation settings. Suffice it to say, they are not too favorable to the method. There is a lot of covariates, there is wild distributions, there is wild transformations that no reasonable analyst would use, and we don't actually assume that you know how to transform the variables in the analysis I will show. So we show results that the analyst doesn't know to put square roots over there. We even have a lot more results that I won't show, where there is very big variances or adversarial transformations. The results seem to be pretty stable, so I'll show just a selection. So this is the behavior of the methods when the outcome regression is correct and when the outcome regression is incorrect. And by the way, just to keep it simple, these are results for the case where you only have the trial only and the external data. So only two, not just k equal 1. So only two estimators, trial only and the external data. Our proposal is the green one, lower is better, and you can see that it remains competitive always, but in small to modest sample sizes, it is actually the dominant method. The estimator up here that's really bad is the unadjusted estimator. So in the interest of public health, if you want one recommendation, don't use the unadjusted estimator in analyzing a trial. Find a way to use the covariates. These are robust to misspecification, and they have much more favorable variance behavior. Now, I did want to show, because we thought, and this is Andrea's work over there, we thought it's very exciting to see how the lambdas adapt to account for characteristics of the data, including the degree of misalignment between the external data and the trial, as well as the sample size, the relative sample size of the trial and the external data. So this gets to the point of sample size. What happens is, if you are at 0, the way we set up the lambdas, you are using the trial alone. So this says, as the sample size increases, you progressively, you go from right to left and end up at 0. You learn to ignore the external data. That's kind of expected, because if my trial is very big, such that I could get a reliable answer, I don't want to be messing with the external things. But you saw there were improvements in variance all the way through. The second way in which it adapts is it adapts to the degree of misalignment between the external data and the trial data. Here we have parameterized a so-called lack of transportability assumption, basically making the external data a little irrelevant for the trial in terms of this delta. And what happens for a fixed sample size, as the delta is smaller, as the amount of bias is bigger, As the delta gets bigger, it learns to ignore the external data. Again, desirable behavior. You want it to learn to discount the external data when it feels that there is more misalignment. And we do this in a data adaptive way. Notice that for every one of these scenarios, you still are unbiased and have good variance performance. This is just showing why you have that good behavior. You have it because you adaptively learn how much weight to put on the external data. This is the most critical slide, perhaps, for practical use of the methods and also for our colleagues at the FDA. The way the philosophy of clinical trials has evolved, and I'm not taking a position on that philosophy right now, I'm just dealing with what is out there. It's critical to have good coverage probabilities for your point estimates. It's good to have tests with nominal false positive error rates and all these things. There is a heavy hypothesis testing flavor in the dominant philosophy for clinical trials. So we felt it's really important that we can show very good coverage behavior empirically for our methods. And you can see here that once you get to 100 people or so, you're basically looking at 0.95. It jitters a little bit, but it's because the scale is blown up. We would be delighted, I think, to have 0.945 coverage in a way under adversarial situations with possibly misspecified outcome models and misaligned data. Okay, now this is simulated data, so perhaps not very exciting, but I wanted to show you that we can get benefits. Sometimes this is 14% benefit. This is average over many runs of the simulation. The amount of the benefit, the percentage benefit, declines as the sample size increases, again, because the trial starts being just enough to do the problem. But under misspecified models, actually the gains behave differently. So this one is under correctly specified outcome model, which gives the best chances to the trial to work out. If you knew the true outcome regression and you just got a bigger trial, you would be fine. Here, with a misspecified model, even as the trial gets bigger, you're not guaranteed to have the most efficient estimator. And so here you can see the benefits keep adding up. Now, proportionately, they're smaller. The regime that appears to give the most benefits is in the 100 to, let's say, 400 or so people. But of course, if you could save 100 out of 400 people, that would be huge. This is simulated data. The realism is not guaranteed. I'm going to show an application in a second. Okay. Actually, I will show two applications. One I show mostly because, to my mind, it's kind of crazy. Let me say why. This was the first empirical attempt we did at the methods. And we said, oh, look, there's this source of social science type experiments. These tend to be relatively big experiments, but it was hard to get appropriate external data for each of these experiments. I don't work in that field, so we had to come up with something. And what we came up with, we said, well, these are experiments where the outcome is something like a human feeling or preference. Just to give an example, you want to help people vote a little more. So you may test out an intervention where one condition is showing a video that talks about the importance of voting in a democracy, and then you may show a pamphlet or just standard of care, if you will. And then what you do is you ask for the people's attitude toward voting at the end of the experiment. And so what's critical about this, what makes this work in this case, is that this is about how humans feel and think. And I have bad news, we are very predictable. So what we did is we took entirely off-the-shelf large language models, no additional tuning. And what we did is for each of these experiments, we subsampled people and we ran through the off-the-shelf model the covariates of the person, and we gave the model the information that the person would be exposed to under treatment and under control. That is to say, let's say for me, we gave all the characteristics of me to the model in a prompt, and then we said, what would this person's answer be about their attitude toward voting were they to see this video? And what would be their attitude were they to just get the pamphlet? Okay? And then we told them the models, we did a lot of them. At the time, these were state of the science, and we did it repeatedly with each one of them. And we told them, tell us what you think this person will feel. What would be the person's outcome? And I will say about these models, which was a little scary at the time, they were actually better in some cases than models developed internally in the trial data. The reason, I think, is these models have seen essentially everything humans have ever written, probably including Twitter, although I wouldn't know. And so they can bring that external information into the analysis of the trial. And it turns out that even though those models are not perfect for each of these trials, they do carry a lot of information about humans from their external training. And then what we did is we compared our estimator using these different models against difference in means, which is the plain unadjusted estimator, the standard AIPW, something called prediction-powered inference, which essentially uses the large language models, but doesn't offer the robustness guarantees that our method offers, and a competing method called PROCOVA, which essentially does a regression in the trial, but with a smartly constructed covariate that is estimated using the external data. And this is the results that we found when we were subsampling 75 people. So what we did here is we said, okay, suppose the trial was 75 people. Repeatedly sample 75 people, or 100 or 200. In each of these, perform the analysis and see how much sample size you could save versus 75 in the graph, or versus 100 and 200 in other results that I'll show in a minute. How much sample size could you save to get on average the same precision as the trial would? And you can see in the 75 case, sometimes there is impressive benefits of 20%. I would say expecting something in the 10 to 20 range is not unreasonable. And here I have a more formal comparison of different methods. These are the different experiments, so each of these blocks is a different experiment. This is subsampling 100 or 200 people. And what I show in blue is the base adjusted AIPW in the trial method. And then red means doing worse than that baseline, and green, or I don't know, yellow-green means doing better because smaller variance is better. And then bold is the best method in every of these scenarios. And so you can see, with perhaps one exception, we tend to do really well compared to the alternatives. And I will just point out that in practice, unfortunately, the blue is not the most commonly used baseline. I would say the difference in means is the most commonly used baseline, and you can see that often it performs worse than the standard AIPW, and we tend to do better than both. Now, a lot of things to doubt here. What are these LLMs doing? Will LLMs work for human biomedical data? Probably no. We're trying to find out. So what we thought we would do, and what I wanted to share with you, and this will be the closing slides of my presentation, is try to apply this to a relatively old trial with some very nice characteristics. Unfortunately, even though we are trying to do this in many modern trials, I cannot share those results right now. So this is a trial called the Coronary Artery Surgery Study. It had a total of 2,100 trial-eligible people identified, and of those, approximately 780, approximately 800 agreed to participate in the trial. But what makes this study unique is for 1,300 people not in the trial, they kept track of their outcomes, they kept track of their baseline covariates, and this is a really nice data alignment situation because the non-trial participants were seen in the same research centers as the trial participants. There was a common protocol for data collection, so we have the same baseline covariates measured in the same way. There was a relatively large number of covariates. Here you can think of the number as about 40. There was near complete follow-up up to 10 years, which is impressive, and the sample size was not too small. Now, before we look at the results, this is not a best case scenario for the methods, even though the data is really good, because we're trying to predict an outcome that's 10 years out using just the baseline characteristics. And so the predictive ability of even very flexible data adaptive methods cannot be really good unless you had much more covariates, much more detailed covariate information. So what makes it A little challenging is this big distance from the final outcome that goes all the way out to 10 years. Okay. Now, parenthetically, this I show to show how we chose the regression method that we applied in the trial. We have some classics like logistic regression in the trial data and in the observational data. We have XGBoost, a tree-based type method. And then we have something more recent that my friends from ETH had to teach me about. This TAB-PFN is basically a deep learning model that uses a prior, constructs a prior, has constructed a prior based on massive artificial data. And the reason I show this is because in our hands, in several applications, it has dominated in terms of mean squared error, methods that I thought were the standard. So XGBoost, I think, is the main off-the-shelf for discrete data, or random forests that would be very similar, and it tends to do better than them, sometimes meaningfully so. And so all the results I will show use the TAB-PFN type of approach. Now, these are the results in the full trial. We have our proposed estimator, which, by the way, we call hybrid AIPW, at the bottom because it was the smallest average confidence interval width or variance, estimated variance. And then you can see that the other methods have bigger, wider confidence intervals. This is in the full data, so it's a one-off. Now, the differences are not striking, but I told you it's very good data, and the trial is sizably large. The event rate is about 20% if you go all the way up to 10 years. So perhaps the asymptotics have kicked in. But what would happen if you were working with a random subset of 100 people? Now the differences, I think, become very material. My point is not to say that this trial should have enrolled 100 people. It is to say that if you were intending to run a trial of 100 people, possibly in a different condition with different variance characteristics, you can experience very sizable benefits by using regression models estimated here in the observational data. This just shows the variance over repeats of the experiments. And you can see the HAIPW, the method we propose, tends to do really well. Once you get to the near asymptotic behavior, there is not big differences, except the difference in means is definitely not the best. And then in smaller sample sizes, you can see meaningful differences. And an interesting curiosity that I found a little surprising is that in small enough sample sizes, the unadjusted can work better than the regression. I think that's because the regression here has too many covariates for this number of people, so it tends to be a little unstable. This is our calculated sample size savings if you were to use the method. And so you can see the proportion of benefit is much bigger if you work at the 100 or 200. This is 20% improvement, very meaningful, I think. But even here, if you think the median cost of a trial participant, I don't know in this specific trial, but overall trials, the median cost is $50,000. This is a sizable amount of savings in terms of research economy for a trial of 700 people. In fact, what happens is because you kind of save a proportion, the proportion may go down, but the number of people gets very large. So I would say if someone intended to run a very large trial, they could get certain benefits in using the method as well. And as I promised, just to summarize first the technical contribution, the idea was trial augmentation. It appears in our hands now to improve efficiency of trials by integrating predictions from data-adaptive external rich observational data. It provides substantial precision gains. We think 20% is not an unreasonable thing if you can have highly predictive, rich external data, and importantly maintains validity of statistical inference without additional assumptions. Just to say what we hope to do for the next few years in terms of the overall research program, the combining information program, not just the augmentation. Augmentation is the new and exciting thing, so I will talk about it first. There is a lot of technical development to do survival, time to event outcomes, to account for complications that would come up in large-scale pragmatic trials like loss to follow-up and non-adherence. There is a lot of work to be done in getting the simulation behavior of the methods. And as I said, we have engaged the FDA and a number of sponsors who have interest in deploying the methods, and we're hoping that this will create projects here at the school and at the Smith Center. The FDA has expressed enthusiasm in being a collaborator on the project, so we're going to try to see if this actually works. In terms of clinical applications, this would cover transportability and the benchmarking and joint analysis ideas that I covered before, as well as augmentation. We see increasing interest in these from our clinical collaborators. As I said, we have a pretty extensive, mostly NIH, but also sponsor-funded research set that tries to deploy the methods in new clinically important clinical trials. And then the last thing, and if my exposition and slides are a little less polished, forgive me. On Monday, we had to submit our final report for the pilot phase of what we call the Raptor CID trial. I am MPI on the trial with Dan Kramer at the Smith Center. The report that we had to submit is the one that Picori, the founder, will use to decide the transition to the full-scale trial. That will be a 5-year, 3,000 people trial. And so the weekend had to be spent on working on that report. I'll tell you how it goes in a few months, I guess. But the trial methodologically is also very exciting, in addition to being clinically, we think, very useful. Why? Because the participants in the trial are nested in a collection of local registries. So the participating sites, of which we hope to have 20, are major cardiovascular electrophysiology centers across the United States. In those centers, we hope to recruit roughly 150 to 300 people per site, and then each site has an underlying population of at least 5,000 people who would roughly be eligible for the trial. And so there's a lot of possibility for methodological development, including augmentation, since the trial that we are designing with Dan is embedded in such a system of rich data. That's it.
Issa, thank you very much for this great overview and really new work. It's very impressive, I think. We have a bit of time, not much because there's another group coming, but a bit of time for Q&A. Whom can I give the floor for a question or a comment? Let's go to Tyler Vanderwele. Tyler, please.
Issa, thank you for a wonderful presentation, very exciting work, very impressive results. I mean, the principal result really seems very beautiful, very powerful. That this is more efficient than any of the component models, including from the trial itself. The one place I wondered whether yet further efficiency might be gained, though I'm not sure if it's possible to automate the intuition, would be if you do have multiple external data sources, and they're all quite different from one another, and you're getting similar predictions from each of them, you might then think, well, the relationship between the covariates and the outcome are relatively consistent across these different populations, and so probably, not necessarily, but probably so in the trial itself. And you may then want to give more weight to the external data than you would if you were getting different predictions. Again, I don't know how to automate the intuition, because how do you characterize the heterogeneity across the external data sets? Maybe kind of the across data set variability versus the within and the primary trial. But I was wondering if anything along those lines might be possible.
We will take any idea, because this seems to be an area for exploration. What I will say is we have some theory for the finite sample case that I didn't go into. Of course, in finite samples, there is no guarantees. That's why we are really prioritizing simulation-based design for real trials. But the theory suggests that, as you seem to be intuiting already, the benefits come if you can find models that basically one explains what is not explained by the other. So even if you see similar predictive behavior, as long as the predictions that they do at the individual level are different, which means one may be capturing something that the other one is not for some observations, you seem to be able to get some extra information. And so we're playing a lot with ideas in that space, like orthogonalization and trying to parcel out one model. But right now, I don't have an automated way either. Yeah. That's great.
Further questions? Please go ahead.
So the
Final time.
data, the external data can have unobserved confounding,
Yes.
and then the assumption would be that the lambdas would detect this and go to zero for the external model.
Yes. Empirically, that seems to be their behavior. But the idea is we find the minimum variance without assuming that the other one is more efficient. They're both, what makes it click is that they're both unbiased if you construct them carefully, and they are definitely asymptotically consistent. So you basically can take the risk without taking a big penalty once the data set is big enough.
Dr. Dahabreh, thank you very, very much, and we look forward to hear about your Raptor results. Well done. I invite you to our seminar next week, which will be different because not here, but only online, and it will be, we'll have Dr. Tim Lash as the speaker. See you then. Thank you very much.